Hello everyone, hope you all are doing good. I welcome you all to a brand new episode of GITA and I thank you all for staying connected to our channel and I hope you all are being benefited to this channel. First of all, I would like to thank our Honorable Vice Chancellor Garu, Professor PVGD Prasad Reddy Garu, for giving this wonderful opportunity of hosting this platform, which is benefiting students and scholars and faculty as well. I also want to thank our beloved Principal Garu, Professor Perry Srinivasarao Garu, for encouraging students to host this platform as well. Today, I am very privileged to introduce today's speaker, who is none other than a very renowned scientist, Devarkonda Sangameshwar Rao Garu, who studied MSc in Andhra University and also did his research in Meteor with Meteor wind radar and also worked in DRDO since 1979 to 2014 at his full capacities, at various capacities, sorry, and retired as an outstanding scientist. He also worked as the chief consultant to the BrahMos and also as a DRD fellow, DRDO fellow, and now he's working as a honorary professor in Andhra University College of Engineering. I hand over the screen to the speaker so that you all get benefited and at the end you can also post your questions in the comment box so that the speaker will address. Over to you, sir.
Good evening, everybody, and thanks for the opportunity given to me for addressing the students, faculty members, to everybody, VC sir, principal sir, head of the departments of electrical and ECE, where I'm positioned now as honorary professor. Now, the coming back to the topic, having spent most of the time of my career, I will be giving the concepts which are used generally in the defense and satellite communication systems and the technologies which enable the development of the systems. I still remember my college days in 1975. There was an article on Hindu main headlines, front page. Communication possible with 100 watts over a distance of 2000 kilometers. The communication signals, basically an RF signal was received at Andhra University. That was when I was studying MSc final year. It was a because 2000 kilometers having a communication with a small power during those days was a huge news. So it has come on to the Hindu headlines. Again, while I was doing research in Andhra University and working on the Meteorburst radar, there was a modeling techniques which are being developed for ELF and VLF communication systems. That is basically communicating over waveguide technology between D layer and the Earth's conduction layer, and we can have a communication globally with which enables communication between ground and submarines, underwater submarines, underwater objects like vehicles or whatever it is, unmanned vehicles or submarines like that. That has prompted my getting into having worked on the meteor vent radar, which is basically a Doppler radar to study the ionosphere wind speeds at the height of about 100 to 120 kilometers by studying the Doppler frequency variations and measuring the way. That was my topic of the research. But without completing that, I have got the opportunity to move to the working as a defense person. And my first assignment was Meteorburst Communication Systems. Why I am telling all these things is because of my love for the institute, which has given me the bread and butter for the next 4 or 5 decades. And still I'm energetic or trying to be useful to the people. So that Andhra University, with a namaste to Andhra University, and the people who are responsible for making it so huge. Now, coming back to the subject, I will not get into the real system details because they are all classified. But mostly, I'll be dealing with the trends which are available and where we are strong and where we should fill the blanks and make it an international power, at least in defense communications. In the sense, the technology readiness level of the systems is very important. This is a technology readiness level. Generally, we get satisfied by doing small things and trying to conclude that we have achieved a lot. This, as a part of the pep talk, I would like to advise to the students. And when you are going up and in your career, the technology readiness level of the most of the systems on a scale of 1 to 10 or 0 to 9 or whatever it is, unless we cross the figure of 8 or 9, the systems cannot be deployed in the user's premises. Generally, we have the capacity to go up to 4. That is actually number 1 level is about the concept, which we write the design on a piece of paper, try to make the breadboard level design, then come to the lab models, then system integrate, then environmental testing to meet the specifications which are required for a very drastic specifications of combat systems. I have this request to all of you when you will be progressing in your careers. Try to reach up to the 8 and 9, then only declare that we are ready with the systems. We have this issue of declaring the things that we achieved and don't do much beyond and depending on the imports. So this is my humble request to all of you to not to get contented with the development at very intermediate levels. Now, this ELF and VLF frequencies, which uses the for the underwater submarine communication, it uses the D layer as a reflecting layer. And actually, the idea came, the whales, if you know, they communicate over long distances from South Pole to North Pole, or I mean, over 3,000, 4,000 kilometers using these ELF frequencies. People have picked up those ideas and they started making, but very difficult aspect of this particular frequency band is, as you know, the wavelength is very large. So the antenna structures will be huge. So they are all installed at the shore level and the communication is taken. And we started this work at a meager 50 bits per second communication levels. Now, the state of our technique is we should be able to go up to 800 bits per second. You may be wondering when we are talking about gigabits and terabits, what is this 800 bits per second? But even this 800 bits per second communication is very crucial for underwater platforms. The reason is that the only wave which can penetrate through the sea waters down deep where the floating of these platforms happen is possible only ELF and VLF. So basically the commands go. We are trying to develop some two-way communication also at very low data rate and the reverse side. That is one aspect of it. Now, as you know, as you go up, then we have the HF, high frequency communication. Still popular. Of course, I'm not getting into the very old Morse key transmissions and on off keying, like those issues. Now, HF is still popular. Many radios are still being developed under combat net radio using the HF frequencies for a long range communication, especially ground to air communication, where the pilots they use still this HF communication systems. Now coming back to the VHF was the most respected and most loved frequency band because we had the line of sight communication over short distances and Meteorburst communication. Why I'm saying this is here the concept is something like this. You might be seeing in the nights the shooting stars. When they are entering the Earth's atmosphere, they burn. And at the heights of ionosphere levels, they cause ionization. That ionized trails are used for the reflection of the radio waves around VHF band. From station A to station B, we can have communications up to 15,000 to 2,000 kilometers. The most important aspect of meteor-burst communication is its survivability in an event of nuclear explosion. Because in an event of nuclear explosion, there will be some disturbances in the ionosphere. It will take a few hours to recoup, and the ionosphere, the communication through the where we use ionosphere as the medium will not be able to sustain. So the embassy is one of these communication system where we can use this in the event of a nuclear explosion. But of course, as a peace-loving country, we generally don't get into the development of all these issues. That is one issue. Second issue is most of the radios now, which are a fashion in the army or the combat net radios, they are actually the man-pack radios as small as possible, so that that will not add to the burden of the soldier. And you must be knowing the concepts of the soldier as a weapon in the sense that a soldier will have all required means like weapon systems, navigation, communication, everything. And this combat net radios and the software defined radios where you have a frequency hopping technique. By the way, I would like to come back to one aspect of it. Most of the defense communication systems depend on the security. Security is there are two levels of security. One is the channel security, where the signal is not difficult to get intercepted. The second one is the information security. Even by chance is able to break the channel, then come back to the data level. Data cracking, that is another layer of security. So the frequency hopping networks and direct sequence spread spectrum techniques are key to the defense communication systems all over the world. Whoever boasts that I have got a secure communication system militarily, he must be having all these features embedded. A lot of work is happening, and I would like to give you the work which is happening all over the world is to achieve a frequency hopping rates of 5,000 to 10,000 hops per second. In the sense that if we are able to send one bit of information, that may be half over one or two frequencies, or at least the threshold is one hop per bit. In the sense that one bit will be transmitted on one frequency, next bit will be transmitted in another frequency. The code is very strong. It will be difficult to be intercepted because you need good correlators, a huge number of correlators to identify these frequencies. That is one aspect of it. The second aspect of it is, if you want to jump, you need a large, wideband amplifiers. The moment you go for wideband amplifiers, the effectiveness of the jammer will come down. But of course, there are other techniques. They're called follower jammers. There, where the frequencies will be followed by the jammer, and they will jump in the a fraction of time of the bit, so that the information does not reach the other person. But most that's the reason why the speed, hopping speed, because there is always a limitation of the interceptors to detect the frequency. Whereas while the transmission side, we can always change the frequencies at our will and wish. But for an interceptor, it will be difficult. So the state of art as of now is going from 500 hops to 5,000 hops to 10,000 hops. The other spectrum, wide spectrum technique is that spread spectrum technique is direct sequence, where we increase the signal bandwidth by correlating with a large wideband signal, or basically pseudo random noise, and transmit, so that this it is signal is spread over a large bandwidth. And again, if you want to jam that particular signal, you have to use a wideband amplifier. Wideband amplifiers or wideband jammers, along with the antenna, which is a wideband. These two are making the life very difficult for the enemy to intercept, because any information, if he is not able to intercept in the real time or within a few minutes or hours, so it is as good as it is not intercepted. That is the secret of the secure communication systems over man-pack radios or combat net radios. Another concept in the same bands around VHF, I will talk VHF initially. The same concepts are extended up to VHF and UHF also. Whatever I'm talking about to be frequency hopping or direct sequence, they're all put together in a same radio, starting from HF to UHF. They are called software defined radio. The hardware is fixed, that has to be configured, because you don't need to change the system depending on the frequency. So it is a software configurable by using the software program, and you should be able to do all the operations on a single inventory. Same radio will be used for all the things. Of course, here the wideband antennas, these are the critical technologies which are under development in various countries. In the same way, VHF radios, I would like to tell you the latest developments are cognitive radius. The cognitive, why I am telling this cognitive importance of the cognitive radius, as you know, the spectrum is fixed. So the number of users will be limited. The cognitive radio is the one which actually sees takes into the cognizance of what is happening around, and see for a window which is available for having a communication with his interested party. There is a communication, and exploitation has been done of the resources to an optimal level. This is the concept of the cognitive radius. These concepts are mostly used for HF as well as VHF and LOS links. The other one is the adaptive systems, where depending on the channel conditions, they change the parameters in such a way up on their own. There will not be any man-made requirements, operations. They will adapt to the availability of the signal channel conditions. They will change from high data rate to low data rate. These are the things like adaptive systems. Another one is the ad-hoc networks, where you see the most of these systems will work under network configuration. In the ad hoc network is that the network's parameters are not defined. They work in an ad hoc way, And the moment they enter into a particular network, they adopt to that network. This is one aspect of it. This is the story as far as the VHF is concerned. Now we come to the UHF and microwaves. You know, I would like to make one statement. The revolution in the military affairs, it was the concept about 20 years back. People were talking about it. But I should say, revolution in the defense communication system has started with the application of satellites for the communication in defense. So we can define in such a way the modern, at least as of now, we can define that pre-satellite and post-satellite are the borderlines where there is a quantum jump of applications with the advent of the satellite communications. Starting as a scientific fiction, it developed into the operational systems, and of course, the advanced countries they had the capabilities of developing large satellites with deployable antennas, whereas countries who are developing countries, they have to live with the small deployable antennas and other things. You can understand that there are some countries where they have got antennas on the satellites, which is of the size of the football field, whereas people are still struggling to have a deployable antennas of 5 meters, 10 meters like that. So this particular advantage, what the advanced countries have got, is difficult to break. And that size of the antennas that has given the advantage into the mobile satellite services. They are called UHF satellites, where the terminals will be having a broad beam antennas, and their mobility has gone up like anything. So if way back, about 30 to 40 years back itself, 30 years back itself, Defense Communication Satellite Program of US, they have used this UHF communications. But because this UHF and S-band are classified as the military communication bands, all developing countries have to struggle to exploit only the civilian frequency bands, not able to pass through the military applications like X-band and UHF. But hopefully, other countries also will have its own launching capabilities, and they will be able to develop the communication satellites so that aeromobile terminals, because the UHF, why I'm telling is that unless you have a broad beam width, you cannot have aeromobile terminals. Number one. Number two, aeromobile requires smaller Doppler shifts. You know, the Doppler shift depends on the operating frequency. So as you have a lower frequency of operation, you will have lower Dopplers. You will be able to demodulate it properly within a small hardware. This advantage has been there with the developed countries. So people should come out with UHF satellites and X-band satellites. Of course, now people are going up to the millimetric wave, Ka band, Ku band satellites also. Now coming back to in the UHF and micro, in between, before the advent of the satellite communication, there was a troposcatter communication. It was largely used by the Army, Air Force. That is between, that also gives trans horizon in the sense that up to 200 kilometers, 300 kilometers communication, which is beyond the line of sight communication, the troposcatter. There are two techniques which are very important as far the troposcatter communication is concerned. See, the common volume is huge for the reflection or refraction, diffraction, or whatever you call of these radio waves. So you have a multi-path. To mitigate that multi-path, you need to have the adaptive equalizer technologies and diversity technologies. both space as well as the frequency diversity. I'm giving you all these words, keywords in such a way so that you will be walking through these keywords so that you will be able to make a small understanding of what was happening over the decades. That's what I'm was trying to impress on you. The pre-satellite communication and post-satellite communication, the developments are very slow. Pre-satellite communication requirement is same whether it is World War II or even at present Ukraine developments. The communication requirements are will be same. People will be looking for real-time situational awareness. If you want to have a real-time situational awareness, you need strong communication backbone. Unless you have, I remember that I visited one of the NATO sites where they were able to see what was happening in Iraq or Afghanistan. I remember, or vaguely remember. That was in 2004. To have that, to reach that capacity, how much the NATO countries have worked and how much, what was the infrastructure. The reason is that fortunately we are a peace-loving country. We work within the four domains of boundaries, whereas NATO and its leader, they work all over the globe. So the resources what they have poured in this infrastructure for either image collection or situational awareness or the communication, security, and their main idea is to reduce the loss of the manpower and the speed with which information is reaching the decision makers so that the people who are working at the work field, they are not denied of the safety. So decisions are taken fast. If you remember Iraq war, the first time Iraq war, US had some jitters. The reason is that they had the countermeasures for against the navigation or something like that. But when the second time when they went there, they learned this interception things, jamming things. They could overcome all those difficulties. They hit it at Iraq. So, as I was telling, communication resources have to work against a strong EW, strengths of the enemy. EW is growing like anything. Fortunately, in the electronic warfare field, we are also a very advanced country. I mean, there's no doubt about it. And communication, the electronic warfare has got two components. One is the communication EW, and the other one is the radar EW. EW systems which work against the communication are called communication EW. EW which works against the radars are called radar EW. In this field, we have to get a strong the communication and the global warfare. If you look at it, we need information about the enemy's strengths and weaknesses. Then only our communication systems, our EW systems will work better. And there, the satellite communications and satellite imaging satellites have come hand in hand for the military powers. Those who are doing a wonderful job on imaging satellites and pinpointing whether there is a soldier or whether there is a tank or whether there is a huge airstrip, whoever is able to identify these objects, they are able to destroy and penetrate the enemy territories. Now, coming back to the subject which we are, after the tropo, slowly the micro LOS links have been come into the picture. But the problem with the micro LOS links are you need repeaters like what we have with the mobile repeaters. So even if you want to have a along the border communication or whatever it is, during where the soldiers fight. So the repeaters are vulnerable because they are large. They are vulnerable for the attack by the enemies. So all these things were eliminated once we have come to the satellite communications. So satellite communication changed the scenario of the information warfare or the communication warfare. Now, in the SATCOM, there are now I'll spend some time on the satellite communication systems. The first we started with fixed with a large antenna, 6-meter dishes. Slowly, that is actually point-to-point communication. There was no network concept, pre-assigned frequencies are pre-assigned. Of course, it is a whatever is the uplink and downlink frequencies. For most of the time, we were exploiting only the civilian satellites. See, that's the advantage we have. We never developed the military satellites for communication or whatever may be the reason. But we could exploit the civilian applications for the defense applications. That's one advantage we had, so that we never got into any problems. But slowly we developed various systems, which slowly we developed into a major defense satellite communication network. Similar to almost close to developed countries. But as far as the mobile satellite services are concerned, we are still lagging. Mobile satellite services, initially they were done with a simple mobile satellite services where handheld terminals are to be developed. This also is a part of civilian application only, not with respect to the defense. Slowly, things have changed. Small developments are taking place. So, mobile satellite services also we started exploiting the in the for the defense. Here there are two concepts. See now, as it should be as small as a mobile terminal, like your for 4G smart mobile. We should be able to come out. So they have used their there is supposed to be a development process where you have same 4G type of terminal in your hand. As long as you have a terrestrial link, you will talk to on the terrestrial link like our mobile conventional mobile systems, where there is no repeater availability. Like we find now signal, there is no signal, that bars are not there. Immediately it takes over into the satellite communication because satellite resources are very costly. But with this dual operation, one is for the mobile and the other one is the through the terrestrial and the other one is through the satellite. This development is should have been done. So wherever there is a, especially if you look at it when you go to the places, you will find about 40% of the places there is no mobile coverage, especially if you look at the border areas because of the strategic requirements. You can't have large structures because you become vulnerable. So at that point of time, this type of systems could be very useful. Slowly, we got into the development of things and maybe small terminal to the slightly bigger. Power is requirement, transponder behaviors. All those issues have to be looked into. Here, one advantage is that the wideband CDMA concepts are supposed to have been used here. Some of the countries they have used the wideband CDMA concepts, so they have used this dual communication techniques, one through the terrestrial, the other one is the satellite. Fortunately, in the satellite communication, mobile satellite services have been exploited, and it is giving a reasonable mm, application and utility for the services are concerned. Now it comes to the other important aspect of this satellite communication is it enabled the network-centric warfare. There are different types of networks like hybrid, star, mesh, whatever type of it's a combination of both star and mesh is called hybrid, where you have a point to point or point to multi-point or through a central hub like this. And one point important aspect I was trying to say is these MSS satellites, they work on double hop. They use from the mobile terminal a lower frequency band, so that the mobility is available and it's always looking at the satellite. And because the powers are limited, the signal is brought back to the ground through a hub with two transponders like C crosses and S cross C transponders. The frequency translation takes place, come back to the ground with a large aperture antennas. The signal is boosted and again sent back to the after demodulation, the information so that the efficiency of the system will go up. Again, retransmitted and C crosses transponder is used. So the terminal to terminal communication takes place. I hope you are on with me on the same wavelength, or if I'm moving fast or I'm dumping so much of, I call it information, you may feel it is a garbage, you can interrupt me. Number one, this type of network centric warfare and the KA band satellite services, KU band satellite services. Another important aspect is the aeromobile terminals using the KO band. It is not only for manned, unmanned. This happened because of the strong stabilization and control system applications, which have come handy, and three-axis stabilizations have taken place. So naval applications, air force applications, with this strong control system backup from various agencies, we are able to come out with aeromobile terminals or naval terminals on the move and without loss of the signal. The fading is not there much. This is another important issue. Now, coming to the other aspect of it, I will give a small glimpse of what future is there. Till now, we are working on geosynchronous satellites. Now we should come back to the work of small satellites in large numbers. Of course, you must be going through the Google and you must be knowing America is very well advanced. They want to have an internet using a small terminal directly to the satellite. Like Iridium started, it failed because of the cost involved. And but we are not yet ready for it. The reason being, the lot of research has to come from universities, and lot of small developments should be done by the universities with the small satellites, starting from nano satellites to micro satellites, and the concepts. I'll give you one small idea. Earlier, the US and other people, they were trying to talk about hopping transponder, in the sense that a conventional hopping uh, transponders will be there, signal will be hopped. Whereas I was just thinking that why can't we launch a microsatellite or a nanosatellite? Just use a single user, tune the frequencies in such a way that it covers the 500 megahertz bandwidth, and look at the possibility whether we will be able to do it or not. This type of applications should be studied by universities as a first cut. After studying, and because the moment you want to you get into the development of large satellites, this information what works like using one oscillator for complete 500 megahertz bandwidth and use for security, because you are hopping the same signal over the complete 500 megahertz using a single elbow. One more, this is one aspect of it I want to study. I want this study to be taken up by the, as for the communication is concerned, by the on our Andhra University faculty. I think head of the Department of Electrical and head of the Department of Electronics and Communication Engineering, with the blessings from the PC sir and principal sir, we should be able to develop this type of applications. This is one application I immediately thought that I will share with you. This is one aspect of it. Second one is that onboard processing satellites. Unless we have the onboard processing satellites, we will not be able to win the wars, because that gives the flexibility in exploitation of the size reduction of the satellite terminals. I'll tell you why. Unless we do the onboard processing, the complete networking, it's a network management system on the satellite. There's no control. Everything is controlled by satellite only. What we do now is there's a network management system, there's a something, all are controlled and sent back to the satellite. Again, they are all controlled by the various terminals, because the terminals are scattered across the country, you can say. Whereas if we have an onboard processing transponder which has got a complete network management system, the situation would be there will be minimal intervention, there will be minimum jamming, and because the interventions come in any means, so it could be a sabotage or something like that. At the moment you put in the satellite, except will become, and another thing is that if you are able to do a bit of security in the channel and other things, that also will become safe. Because these geosynchronous satellites is generally people are not allowed to jam. It is an act of war. So this exploitation should be done by the concerned agencies for making it so fast. Unless we do, I'm repeating the same statement two or twice, because unless we have a onboard processing satellites, we will not be able to make a dent in the this type of architectures. Coming back to the another important issue with respect to the satellites are concerned, intersatellite communication is another aspect which is, it may not be directly applicable for the communication satellite. See, satellites are not only for communication, they are meant for some many applications like the many. I don't want to name all those things because you may be knowing it through the open literature. There will be formation flying satellites which are required for a specific applications. When you want to do the formation flying satellites, you need intersatellite communication. At least the intersatellite communication needs should be probed by at the university level and try to come back with some solutions, like whatever, whether it's called laser communication or millimeter wave communication. This particular aspect also can be addressed by the universities depending on the resources available. And I make a plea that the concerned departments also should be able to fund the research in the universities, so that this will help in their developmental life cycle time, reducing the developmental time. This aspect also should be addressed. Now, this coming back to the 5G aspect. I did not touch much on the mobile because mostly it is civilian applications, but 5G has got a lot of impact on the defense applications. We were discussing about it, how it is going to affect this. That the radar altimeter frequency comes somewhere in this 5G bands, and 5G technology is really wonderful technology. It should be exploited, but without compromising the defense applications. In the interference, all these studies should be done. That interference studies can be taken up by universities again. because we have got talented people, final year students like project work, MTech students, research scholars. Please try to do this type of studies. 5G, how it is going to affect the through its interference. It is interference not only through the direct signal. This is the side bands. You have harmonics. All those issues will be there. First harmonic, second harmonic, third harmonic, whatnot. So this analysis can be carried out by university. Of course, one advantage, as I was telling, that India being very strong in the EW field, the technologies which are developed by through them is a wideband technologies, which like in the antennas or front ends. Those systems can be used for the 5G type of applications in the communications. I request some sort of coordination can take place and can be exploited. Now, because there is a possibility that 5G applications may still go up to the millimeter wave communication. Millimeter wave communication, I'll tell you the reason why it is very important for the defense is the millimeter wave signals fade out beyond the required range. Suppose if you make a link between about 10 kilometers, the immediately about beyond 10 kilometers, by 15 kilometers, the signal is not available for the interception by the enemy. So this particular aspect should be exploited. I hope you understood by this millimeter wave. Another thing is that it has got the atmospheric uh, effect on the fading. And this is another aspect of it. The universities should take care of studies on the studies on the atmospheric effect on the millimeter wave propagation. In a small, it does not require much of infrastructure. Small infrastructure can take place. So this is another important issue. Last but not the least, I'll come back to the end of my talk. I was trying to cover as many subjects as possible. It's only just keywords I'm just putting it. Uh, I'm not sure how much it has sunk onto you. Quantum physics, the principles of quantum physics are exploited for the quantum cryptography. There, the mathematics takes the upper stage, whereas earlier the mathematics was taking care. Here, the physics, the quantum mechanics principles. The combination of mathematics and physics, especially quantum mechanics, should be exploited for the cryptography, quantum cryptography. You know why I'm stating this repeatedly is that this is within the reach of the universities. It does not require a lot of infrastructure. Lots of studies can be done. The cost-effective polarizers can be developed. Cost-effective filters can be developed or experimented at least. Or what is and the cost-effective codes can be developed. How it works is the principles of quantum physics state that the observation of a quantum state causes perturbation. Any attempts by the eavesdropper to observe these transmitted photons will indeed perturb the transmission, and that is detected. So the moment the eavesdropping person is there, that is noticed by the system, and immediately you change the algorithms. So this is the in nutshell, small way. I'm just giving you the concept of this quantum cryptography. This is useful for the futuristic defense applications where we need to have a lot of security. There are two, three important aspects I would like to highlight is the data security, channel security are the key elements for any defense system. I will conclude on this, and I'm sorry, I'm not. I'm just giving you only concepts. You know the sensitivities of being an ex-DRDO person. Uh, I have not elaborated on the majority of the specifications and other things. As you know, um, I should be within my limits. So I will end this talk at this point, and I wish you all the best. And try to concentrate. And I'm there available at the university, and I hope some office is being arranged. I will be accessible, approachable. We will work out on the major projects and programs, and trying to make a small beginnings in this way, so that it works. It helps the defense in a small way, at least. Thank you very much.
Thank you very much, sir, for your valuable talk. I hope all the students and the scholars also benefited from this talk, sir. Thank you, sir.
Okay.
Thank you everyone for joining us this long, and I hope this talk really benefited you and also gave you a lot of information about defense communications and satellite communications. Um, I once again thank our uh, speaker Garu for giving his valuable time. Thank you, sir. I would also would like to thank our professor mentor, Professor Malikajan Garu, and also AU Computer Science, AU Computer Cell, and also Professor Amasuda Ma'am Garu for giving this uh, wonderful opportunity and supporting this platform as well. Thank you all for staying connected. Please share this video with your friends and family so that they get benefited from this talk and also get more insights about defense communication as well. Thank you all. Jai Hind.